So the next speaker is all the way from Switzerland. He's Dr. Petar Tsankov, PhD from ETH Zurich, not to be confused with ETH for Ethereum. One interesting anecdote, I guess, from Hello World's point of view is that when we wanted to do our token sale last year, we went to search high and low for a good security auditor. We couldn't find. We know Loy Lu, who's now with Kyber, who was busy with both Pool and Kyber at that point. Consensus, Zeppelin, all were busy. And luckily, we found out about this team from the ETH Zurich University, just starting out at that point in time. We took a stab at it, and now they're all over the world, presenting at DEFCON 3, at ETHKL, and multiple other conferences, and with multiple services around. So, not saying more than that, I'll just get Dr. Petar Tsankov to talk about how not to get hacked. Please give him a round of applause.
Thank you for the very kind introduction, Harith, and thank you and David for inviting us here. It's great to be in Malaysia to talk about some of the work that we've been doing. So let me first introduce the teams that are working on the project that I'll be talking about. So on the left, you see the research team from ETH Zurich, which is working on the research side behind this, the technology that we're building. And on the right, you see the chain security team. This was shot when we were in Prague a few weeks ago. So what we're trying to solve is, as we all know, security is one of the major issues that exist in Ethereum today. And we've been working really, really hard to make sure that that we mitigate this issue. So that just as you know, only this year, more than $1 billion were lost due to hacks in the Ethereum ecosystem. So in order to fix this issue, it's very important to understand actually what is the lifeline of a smart contract and where security issues appear in these stages. So typically, first, you will start with the development of the contract, meaning you figure out what you want to build and you develop it. And the main issue here is that smart contracts are written in new languages where people are not super familiar with them. Is it on this one? All right, I think that's working. So programmers are simply not familiar with them, and they make common mistakes introducing vulnerabilities. So that's the first major issue. Once the code is done, then, as we all know, the code goes to a code audit to make sure that a third party to certify that it actually correctly implements the functionality that is intended in the smart contracts. And once the audit is done, it is deployed on the blockchain, and users can start using the smart contract. So the main problem with the code audit phase is that currently most of the audits are actually done purely manually. This means that people manually look at the code line by line and try to figure out if it correctly implements some functionality. So what we're doing to fix this problem is we're building advanced automated tools to help developers certify their contracts while they're developing them. We're also introducing something called machine-checked audits. This means that you can use a machine to certify that the contract is correct without relying on people that the code is correctly implemented. And we also have monitoring solutions that would allow clients and users to track what's happening to the smart contract once you deploy it onto the blockchain. So I'm going to briefly talk about the techniques that we're building in this space here. All right, so the first system that we actually started building is in the automated security tool space. We built a usable security scanner for Solidity. And then we also ported this system to Hyperledger. And let me show you what this is. So how many people have heard about Securify? It's one of the, all right, not many of you. So I'm going to tell you what this system does. So the main idea is that you want to quickly detect generic security vulnerabilities. What about the Dow Hack? Have people heard about the Dow Hack? All right, most of you. So this actually illustrates what happened in the Dow Hack. The issue was that you had this transfer of Ether to a contract, and then you had zeroing the balance of the user after the transfer is done. And the issue is that when this call here is made, this actually transfers control back to the contract. So a malicious user could actually take more money than it is actually allowed. So in order to prevent these issues, typically you want to have some kind of security property that captures this unintended behavior. So in this context here, we may want to say that we don't want to have any state changes after call instructions like this one. So in this case, this would be a violation because the balance is set after the call is made. So why is it actually hard to do this? Why is it hard to automatically find such generic vulnerabilities in the code? So let's take the security property as an example. if you take a smart contract, based on this property, I can look at all the co-statements in the contract, and I can classify whether they're safe or unsafe with respect to the property, so whether they satisfy or violate this property. Okay? And then the question is, well, can you actually, given a contract, automatically check for each co-instruction whether this holds or not? How many people think this is possible? Not many. All right. It's actually not possible, and the reason is that smart contracts are written in Turing-complete languages, and this means that it's not possible to decide such arbitrary properties on arbitrary contract. So this is really the major issue here. And when we started working on this, all the existing solutions were basically avoiding the problem by looking at subset of these behaviors. And the problem is that, well, you're looking at some behaviors, which means you can actually miss to report some of the vulnerabilities, which is not really what you want if you want to make sure that your contract is secure. So then we wanted to do better than this, and we had the following insight. We actually looked at many real-world smart contracts and many violations of this property, and it turns out that very often when smart contracts violate or satisfy such security properties, they also tend to satisfy or violate much simpler properties or patterns. So let me tell you what this means in this example. So if I want to make sure that this security property holds, meaning that I don't have any state changes after co-instructions, I can simply look at the control flow graph of a smart contract and make sure that no writes can ever happen after such co-instruction. And this kind of patterns are much easier to check. And this one here in particular, if you actually run it on the Ethereum blockchain, you would see that you can certify 91% of all the co-instructions in the contract. And you can also do the same, by the way, for violations. You can also phrase simpler patterns that capture definitely violations of these properties. For instance, if you see that a write must always follow a co-instruction, then this property is guaranteed to be violated. So this is exactly the idea that we used to build a security file system. It's publicly available here on this subject, so you can go and check it out. And this was just one example of security property that it supports. The actual system implements many other security patterns that you could check your contract against. All right, so that was the first system we built, and this is very useful if you want to target generic security vulnerabilities. However, very often you also care to check contract-specific properties for your smart contract, because when you write it, you want it to implement some very specific functionality. So for this purpose, we built a system called Symbolic Verifier. Let me show you what's the idea here. So what's an example of contract-specific requirements? For example, if you're implementing a crowd sale that is minting tokens, you may want to have requirements such as the owner cannot mint more than 1 million tokens, or you may want to make sure that the amount of tokens never decreases. So you can just list all the requirements that you have for your smart contract. And then the goal is to verify that these requirements are correctly implemented in the source code of your contract. So very roughly, if you want to check these requirements, what is the problem here? So in order to check it, what you have to do is you have to start with the initial block of the smart contract. So this is basically the state of your contract once you deploy it. And then you can brute force all the transactions you can send to your contract. You can see where the state changes into your smart contract. That would be depth 1 of transactions. Then you can do this again, run again a bunch of transactions, and then you have to keep doing this over and over again. And then you have to make sure that in all these states here that you could reach with any sequence of transactions, all the properties are satisfied. That's the core of the problem. Well, that's very hard to do in practice. Why? Because this width of this tree is really gigantic. Just think of all the possible transactions you could actually run on a smart contract. And also this depth is unbounded because your users can send any number of transactions to your smart contract. So that's inherently the challenge that you have to solve if you want to verify these properties. So that's why we don't do this kind of brute force approach, we do something else. And very intuitively what we actually do is we first, instead of running concrete transactions, we run something called symbolic transactions, meaning that you run with symbolic values instead of concrete values. So here my branching factor is now 2. If I have 2 transactions, it's not the total number of transactions that you can send to the contract. And then something that's very critical is you also have to use kind of abstraction at these levels. When each of these blocks is represented symbolically, it captures a number of different states. And if you use abstraction, you could actually guarantee that you get a fixed point of all the states you could reach. So if you combine this symbolic reasoning with abstraction, what you get is you get a feasible width that you can analyze, which is branching on the number of functions in your contract. And you can also get a bounded depth on the tree that you have to explore. That's the key here. So we have built a system based on this idea, and there's a specific language that you can use to formally specify the requirements for your smart contract, and then the system would either verify, not verify, or fail to verify certain properties. So it's a completely black box solution that can certify correctness for any sequence of transaction of any length. So this is the system for contract-specific requirements, and the last system to build was an AI-based testing solution for smart contracts. Let me show you what's the idea here. So again, we start with the initial block of your smart contract, and you want to fuzz your smart contract to see what happens. So intuitively, the way this works is you generate random transactions, you execute them on the contract, and then you get a bunch of states that you would observe while you're running while you're fuzzing your smart contract. And then here on all these phases, you can check your properties to make sure whether they hold or not. So the hard challenge here actually is to come up with what kind of transactions you have to run on your contract in order to get some high coverage over the functionality, whether it's code coverage or any coverage you can think about, any metric on any notion of coverage over your smart contracts. And the key insight that we leveraged here is that if you, instead of doing these random kind of transactions, you could actually use machine learning to learn what kind of transactions tends to achieve high coverage on general contracts. So you can just take a bunch of, say, crowd-sale and token contracts and learn this kind of, get this kind of knowledge. You could also just take the transactions that are deployed on the blockchain and learn from those. And then this way you could get significantly higher coverage. So just to give you some insight of how much better you could do. So if you do random testing, random generation of transactions, you would get to something like 70% coverage on average contracts. And if you do these AI-based solutions, you could quickly converge to much higher coverage over your smart contract. All right, so this is actually the main technologies that we're building for correctness, and I'll briefly mention how we use them for audits. Well, actually, we have built an audit platform that combines all these technologies to provide audits for contracts. So this audit platform will take the contract, the specification of the contract, and would produce an audit report based on the results from these systems. And we have been very lucky to work with many clients, including Hello Goat. That was last year. Right, and the final product that I'll very quickly mention is that we have built a security monitoring solution that could track all the transactions, and you could customize it with different properties you want to check on your smart contract and make sure that those hold. And if something goes wrong, it could alert you to fix these issues. All right, that's everything from me. Thank you very much.